Okay, this is going to be the solutions to workshop 9.3. So let's get started. First thing we need to do is balance this equation. And you, at this point, should pause the video, make sure you solve all three questions, and then start the video to see if your work matches the work that I'm doing here. And that's where the learning will take place. So don't just watch this. You should have tried before you watch, or at least pause the video once you get stuck, see if I answer a question for you or something like that. So let's get rolling here. So you should have balanced this equation first, and that is right here. Your equation is C4H10 plus oxygen, that's butane plus oxygen, produces carbon dioxide plus water. To balance this, I'm going to say I've got carbons, hydrogens, and oxygens. I write that right under the arrow when I balance. I've got 4 carbons on the left side. I've got 10 hydrogens and 2 oxygens. On the right side, I've got 1 carbon and 2 hydrogens, and I've got 1 and another 2. I've got 3 oxygens. So when I balance things, I always try to balance the I like to try to balance the things that are left alone last, because they're the easiest to adjust, where everything else will be kind of a factor, because the carbon's going to affect the oxygen here, and this carbon's going to affect hydrogen. So I'm going to try to deal with the oxygen last because it's alone. So let's just take carbon because it's right off the top. So I need more carbon on this side. I'm going to put a 4 here. Now that gives me 8 oxygens and another oxygen here, so that's 9 oxygens. Now let's balance our hydrogens. I've got 10 here, so if I put a 5 here, that will give me 10 hydrogens, and I've got 5 oxygens and another 8, so that gives me 13 oxygens. Remember, I've got 8 plus 5. Now everything's good except for my oxygens, so I've got 13 oxygens, and I need to increase this to 13, but this is going to be a multiple of 2, so it's not going to work with a whole number, but that's okay. Let's just try it with a non-whole number. So 13 divided by 2 is 6.5. So if I put 6.5 here, that would make 13 oxygens. Now a proper balanced equation should only have whole numbers. But right now it is balanced, so I can keep it balanced and make this a whole number if I just increase both sides by 2. So if I multiply everything by 2, I'm going to say that there's a 2 here, and 2 times 6.5 is 13, 2 times 4 is 8, 2 times 5 is 10. Let's just double check this. Now I've got 8 carbons, I have 20 hydrogens, and now I've got 26. That's a weird 2. 26 oxygens. On the other side, I've got now I've got 8 carbons. I have 16 oxygens here, and I got 16 oxygens here and another 10, so that's 26 oxygens. And hydrogens, I've got 20. So carbons match, hydrogens match, oxygens match. So our balanced equation looks like this: 2C4H10 plus 13O2 yields 8CO2 plus 10H2O. There's our balanced equation. And that was how we worked it out. So number 1, a scientist combines 2.3 moles of butane, so 2.3 moles of butane, to 18.7 moles of oxygen. 18.7 moles of oxygen. Again, if what I'm doing here it seems too fast or confusing, go back and watch the lesson for 9.3. I kind of try to walk through the steps a little bit slower with the lesson itself. This is just the solution, so watch that if this is going a little fast. What I need to do is figure out which one of these, this is a limiting reactant, which one of these is going to run out first. So what I do is convert one into the other to figure out which one's going to run out first. And I'm going to convert the butane into the oxygen. So I'm going to say that 2.3 moles of butane, C4H10, for every 2 moles of butane, there's 13 moles of oxygen, and that's a 2 to 13 ratio. Moles of butane cancel with each other, so how much oxygen is there would be 2.3 times 13 divided by 2, 14.95. 14.95 moles of O2. Now what that says is to use all of my butane, it's going to require 14.95 moles of oxygen. Okay, well the question said I had 18.7 moles of oxygen. Therefore I have more oxygen than I need. This is how much I need. I have more, which means the butane can run out completely, which means butane is my limiting reactant. That's going to run out first. There will be some leftover oxygen. So let's figure that out right now. How much oxygen is left over? Well, we also know that there's going to be no butane left over. That's going to run out. How much oxygen is going to be left over? Well, if I start it with 18.7 and I subtract that number from there, so let's go 18.7, and we're going to subtract 14.95 from it, we come up with 3.75 moles. Remember, this is moles of O2. Moles of O2 would be left over. So we are going to have, this is what we started with. I'm going to put I for initial, and I'm going to put F for final. I didn't start with any of these. And our final concentrations are going to be right here. So I'm going to have 3.75 moles of oxygen left over. Oh, that focusing's really bad, huh? It's like it's breathing, it's pulsating. That's better. All right, so now that I know that the butane is our limiting reactant, I'm going to use that to figure out how much carbon dioxide and oxygen are going to be formed. So we're going to say 2.3 moles of butane, C4H10, will produce, let's do carbon dioxide. For every 2 moles of butane, it's going to create 8 moles of carbon dioxide. So it is 2.3 times 8 divided by 2, 9.2 moles of CO2. So 9.2 moles of CO2 will be produced. And let's do one more. Let's go into water. So water, we have 2.3. Remember, I'm just going to always use the butane because that's what ran out first. That's my limiting reactant. Moles of butane. For every 2 moles of butane, I'm going to produce 10 moles of water. Moles of butane cancel out with each other. So this is 2.3 times 10 divided by 2, 11.5 moles of water. So that's my answer. I'm going to have 0 butane left over, 3.75 moles of oxygen, 9.2 moles of carbon dioxide, and 11.5 moles of water. And with significant figures, I would probably, on a multiple choice test, you would probably see this written as 3.8 moles. This 5 would round the 7 up. This would still be 9.2 moles. And this 5 would round the 1 up, so this would be 12 moles. With sig figs, these two would round up there. Okay? In the second question, we're going to be, it's a little bit more tricky in that you have to understand what's going on. This is more, you have to apply the chemistry in here. You have to know when to use which tool that you've learned. So number 2 is going to be a little bit tricky, but if you understand what's going on, the math and the setup is not that difficult. So in this question here, it says, in our balanced equation, it says that we're initially starting off with 16.2 moles of oxygen. And it says that when the reaction's done, let's take a look here. It says that unknown amount of butane. The above reaction took place producing 7.3 moles of carbon dioxide. The vessel had no carbon dioxide at the start of the reaction. So if it had no carbon dioxide at the start of the reaction, that means there is 0 moles at the start. That means everything came from this reaction. Everything from our reactants produced this carbon dioxide. And it says that we have 7.3 moles of carbon dioxide when it's all final. These guys don't seem to matter in this equation. The butane and the water don't seem to be a factor because the question's asking how many moles of oxygen are left in the vessel. So how many moles of oxygen are left in the vessel? Well, if this was produced from the reaction, we can stoichiometrically figure out how many moles of oxygen were used to produce 7.3 moles of carbon dioxide. So to do that, we take 7.3 moles of carbon dioxide, and let's convert that into oxygen. For every 8 moles of carbon dioxide, you have 13 moles of oxygen. So that would be 7.3 times 13 divided by 8. And I've got 11.86 moles of O2 was needed to produce the 7.3 moles of carbon dioxide. Well, when we take a look at this, we find that, yeah, we had more than enough oxygen for this to happen. So the question is how much oxygen is left over. So that is just simply, if we start it with 16.2, we're going to take 16.2 and subtract, this is what we started with, and this is what we used in the reaction, and this is what's going to be left over, which would be 16.2 minus 11.86, 4.34 moles of oxygen is going to be left over, and with 3 significant figures, we're actually there, so it's 4.34 moles of O2 will be left over. That would be our answer right there. That's all. 4.34. That's a 4. There you go. Okay, on to number 3. All right, so the last question, the question is giving it to you in grams, which is more realistic. In lab, we do things in grams. And it wants the answer in grams, what will be left over in grams. And then there's a second part, calculate the percent yield if the student actually produced 22.5 grams of carbon dioxide in the lab. So there's a lot to do here. So let's get started on this one. So we've got 2 reactants. We got to figure out, the first thing I always want to do is figure out which reactant's going to run out first. The reaction stops when either the butane runs out or when the oxygen runs out. When one of these runs out, the reaction will stop. So we got to figure out which one's going to run out first. So to do that, convert one into the other. So let's convert the butane into the oxygen. So 4.5 grams of butane. And we're going to convert this into oxygen, but it's not a mole-mole relationship now. It's gram-gram. So we got to do a lot of work here. We're going to have to convert the moles of butane into the moles of oxygen. So we're going to go moles of butane, and I will just do this once here. We'll do this over here. Butane would be 4. Let's see. It'd be the molar mass of carbon, which is 12.0100 times 4 So C4 equals 48.00 or 044 48044, and hydrogen is H10. So hydrogen was 1.008 times 10. So we have 10.080. And if we sum these two, if we add them up together, we're going to take that and add it to our 48.044, and I have 58.124 grams of butane per 1 mole of butane. Okay, now I've got a gram to gram cancels out. I'm in moles, but I want to get us into grams of oxygen just to compare how much oxygen will be needed to burn all this butane. So let's convert this into oxygen. For every 2 moles of butane, there is 13 moles of oxygen that's needed. And then let's convert that one more time into the molar mass of oxygen, and oxygen is 15.999 times 2. So this is 31.998 will be the molar mass of O2. I'm going to put that up there just as a little reference because we'll be using this quite a bit in this problem. So for every 1 mole of O2, I have 31.998 grams of O2. Okay, so let's plug that in. 4.5 times, well, let's clear that. 4.5 divided by 58.124 times 13 divided by 2 times 31.998 equals 16.1 grams of O2. Moles cancel with moles, moles cancel with moles, I'm in grams. So what's this saying? To burn up all my butane, I need 16.1 grams of oxygen. I only have 3 grams of oxygen, 3.4. I don't have enough. So I just learned that oxygen is my limiting reactant. Oxygen's going to run out last. So this is my initial and this is my final. I know, I just figured out here, oxygen's going to run out. I'm going to have 0 grams of oxygen because I don't have enough oxygen to burn the butane, so the butane is going to run out first. Yeah, the butane's going to run out first. No, the oxygen's going to run out first because I need 16 grams of oxygen to burn 4.5 grams of butane, and I don't have that much. I only have 3. So this is my limiting reactant. And this is a very important first step, guys, because this means that the 3.4 grams of oxygen determined this whole situation here. So let's get started. We're going to have to convert 3.4 grams of oxygen into butane, into carbon dioxide, and into water. We're going to have to do all those things. The thing is with this one, it's just going to add to 0, but for this one here, we have to subtract that number from 4.5. So let's do the butane first. So 3.4 grams of oxygen. And I already determined the molar mass of oxygen, so I get to use that again. 31.998 grams of oxygen per 1 mole of oxygen. And for every 13 moles of oxygen, I get 2 moles of butane. This is C4H10. And butane, already did that part. For every 1 mole of butane, we have 58.124 grams of butane. And I already calculated that molar mass, so I get to use that again. So this is step 1 here. So let's do this. Let's say 3.4 divided by 31.998 times 2 divided by 13 times 58.124. Okay, so this is saying, when this is all said and done, that to burn all 3.4 grams of oxygen, it's going to require 0.950 grams of butane. So that's going to require this much. So if I take what I have, 4.5, if I take 4.5 grams of butane minus 0.95 grams used, so this is what we started with, and this is what we used. This is what will be left over, will be 4.5 minus 0.95. We will have left over 3.55. So left over we'll have 3.6, we'll basically say 3.6 grams left over. 3.6 grams of butane. Okay, so that's our butane work. Let's convert next into carbon dioxide. 3.4 grams of O2, and I get to kind of follow the same setup I just did. For every 1 mole of O2, I've got 31.998 grams of O2. And for every, our equation up here, for every 13 moles of O2, there are 8 moles of CO2. Now we're going to do the molar mass of CO2, which will be oxygen, which is this, times 2, plus a carbon, which is 12.011. So our molar mass of oxygen, of carbon dioxide, is 44.009. And I'm going to put that number over here. For every 1 mole of CO2, I've got 44.009 grams of CO2. Okay, let's plug that one in. 3.4 divided by 31.998 times 8 divided by 13 times 44.009. 2.88 grams of CO2. And that would be for this one here. So this is going to produce 2.9 grams with 2 significant figures of CO2. And let's do the next one to water. 3.4 grams of O2. We're going to convert this into water, and we get to use the kind of the same numbers we've been doing before. 31.998 grams of oxygen. For every 13 moles of oxygen, there are, for every 13 moles of oxygen, there's 10 moles of water. So 10 moles of water. And the molar mass of water is 2 oxygens, or H2O, 2 hydrogens, 1.008 times 2 plus an oxygen, which is 15.999. So the molar mass of water is 18.015 grams of water for every 1 mole of water. Grams of oxygen, moles of water, or in grams of water. So let's solve this one here. 3.4 divided by 31.998 times 10 divided by 13 times 18.015, and I get 1.47, which would be 1.5, I'm rounding off here guys, 1.5 grams of water. So 1.5 grams of water up here. Now, a good way to double check this stuff is just sum up all of your initial, which would be 4.5 plus 3.4. It's roughly 7.9 grams. Remember, law of conservation of mass doesn't change. And I did do some rounding off, so it should be very close to each other though, but let's see how close I get. 3.6, let's clear that, 3.6, that's this number. Now we're going to add up these numbers here, plus 2.9 plus 1.5, and that's 8. So you can see within the estimated of that last significant figure that they're in range. If I would have not rounded off till this point with 2 significant figures, it would have been right on. So this is a good sign. If you're getting something significantly different, you know you did something wrong. So these are our final values right here. We have 3.6 grams of butane. We've got no oxygen. We've got 2.9 grams of carbon dioxide and 1.5 grams of water. But there's still one more thing we have to do. And look at all the work that we did for this question. It's filling up a whole paper. So the last thing I need to do is it said, what's the percent yield of the carbon dioxide? Okay, so the percent yield is what we should have got. So theoretically, I just did some calculations, and it says I think I should have got 2.88 grams of CO2. But the question says, but I actually got 2.5 grams. To calculate the percent yield of the student, they actually got 2.5 grams in the lab. So percent yield, I'm going to take what I actually got in the lab, 2.5 grams of CO2, and divide that by what I theoretically got by my calculations, multiply that by 100, and that would be our percent yield. So we have, with 2 significant figures, I would say that's an 87% yield. Okay. Hopefully, a lot to do there, but hopefully working it out and talking you through it, you can understand the steps to all this stuff. So there's 2 parts of the answer. This is the first part, and this is the second part. I will see you soon, and good luck chemistrying.